Thank you very much, Mr. Chairman, for that very warm introduction. It's also a great honor to be back here in this very exciting city. So thank you to the organizers for inviting me back again. As they say, once can be considered a mistake, but twice there's no excuse. So I believe this session has been entitled, Have we reached the end? I'd say the answer to that is we've reached the end of the beginning. Once we start to debate how we can improve things, it means that we've arrived. And you know, I go back to those very early days when even the thought of IVF was abhorred. People like James Watson, for example, would say that it should never be allowed. So what we debate these days is how we can make improvements on a wonderful medical science that's changed people's lives for so many decades now. So I want to just take you through some areas, primarily in the embryological domain, that I think we may see in the coming years that might make improvements, and also to give you the experience of our own data, which I think is also fairly relevant in showing how we believe we might be trying to improve live birth rates, not just pregnancy rates. My conflict of interest is that I'm a minor shareholder in the Care Fertility Group. So I think we do need to bring about change. I think change is being brought about. And I think the information that we see here is quite clear, and I base this on the United Kingdom's audited data from 1991 by our regulator, the Human Fertilization and Embryology Authority. We have seen success rates rise considerably by whichever parameter you measure, per embryo transferred, per cycle started. In fact, the HFEA was the one that always said that the data should be provided per cycle started. You can see that we virtually doubled our live birth rates, and the top clinics have more than doubled the live birth rates. And I believe most of that has been brought about by technology. Clearly, one can never substitute attention to detail. That is always extremely important. It's one of the reasons I think why new IVF clinics or clinics that close and restart again all of a sudden see a spike in their success rates. It's always about attention to detail. But the overall lifting as results, I believe, is about technology to a large extent. And we always strive for new technologies. I think the scene was set beautifully by Pasquale earlier today. Because in a sense, his talk is conflicting and importantly informative. And Sherman Silver's paper too on the oocyte in the natural cycle and its very low chance of success. I think in that overall data, I think in all ages, I think the likely outcome was about 14%, which you can see was fairly similar to our early days data. So we have to ask ourselves, well, actually, if it's that inefficient and it's not that good, although we now believe we're doing better than, as Pasquale said, 25% in the young people, the fecundity rate, we can do better than that, much better than that, double that in our IVF technologies. Then we have to be striving to do something better. Because we keep saying it's not good enough, but on the other hand, we should say, well, let's not take on board new technologies, and maybe there's a way to bring on board new technologies, which is a separate debate, the evidence-based medicine. But nonetheless, we strive for new opportunities, and I think because there are two simple truths. Firstly, we know that not all embryos make babies. It doesn't matter how you look at them or how you try. In fact, we've seen data earlier today that it is really a poor outcome on a per oocyte basis, and also it's not a great outcome on a per embryo basis. We know about 70% of them are probably non-viable. We also know there's a large relationship to age, as we see here, and as the woman ages, so the miscarriage rates increase. And we think a lot of this downturn in live birth rate is due to an aneuploid embryo. We've known since The really important paper by Angel et al. In 1983 and another follow-up in 1984 that embryos were aneuploid. It was a great shock there was an incidence of aneuploidy in human embryos, because at that stage most of the work was done on animals, particularly rodents, and we didn't see that level of aneuploidy. Yet today we now know where we are with the increasing aneuploidy issue. And when we look at the origin of that, it is indeed from the egg. And I think that's probably incontroversial at this juncture anyway, that most of the aneuploidy we see is meiotic. The second, I think, simple truth is that we are just too inconsistent. Here's a list which I don't want you to be able to see, so you can't see it and you can't really read it, which is the whole point of it. But that's the list of about 70 IVF clinics in the United Kingdom. And whether you take on the left-hand side the less than 35 age group, or the all ages on the right-hand side, what you will see on however you measure it, per cycle started, which is intention to treat, or per embryo transfer, or per embryo transferred, you see a huge range in outcome. And clinics that are, have been going and established for many years, from, let's say, the less than 35 group of a 50% live birth rate somewhere up at the top, to down to 14% live birth rate in the bottom third, and even lower than that if it's taken over all ages. So really, in a country like the United Kingdom, where you have high audited data, and every cycle is transmitted electronically, you would expect that we could get a little more consistency than we see here. And what's really interesting, if you look at big data analysis, so you compare the US and the United States SART data, actually we see a very great similarity in the average live birth rate between the two countries. It's quite remarkably close. In the US, the latest data that I have is 25.5% for all ages versus 24.5% for the UK. And yet, in both countries, you will see wide ranges. So, for me, if we take this, for example, this commentary from Rosenbach's, published in 2017, Biomarkers of Embryo Viability. Well, he states it's a search for the Holy Grail. If the Holy Grail could be divided, it would be part of the Holy Grail. Search for biomarkers of embryos with quality, and the goal for selecting the single embryo for transfer continues to be the major challenge facing our field. He goes on to say that although one cannot ignore the fact that uterine receptivity is in part responsible for implantation efficiency, it's generally agreed that embryonic factors are mainly culpable for implantation failure. Well, for me, that statement is a self-evident statement, but it's a bit light, because failure happens due to embryos, due to the endometrium, and probably several other female physiological factors too, at the very least. We do need to start to refine the knowledge of our gametes, our embryos, and our patients in order to really up our game. Now, there's a lot of debate, as we know, in the area of what I've started out in this talk about in this discussions, and that's in aneuploidy. And that is, if aneuploidy is there, then should we not try to select out the aneuploid embryos? Now, this is not a PGT-A or a PGS debate. It's just, for me, a factual discussion on where we are with the PGT-A arguments. We have big data analyses, and that is from the SART data, that when I asked them, I actually sent them a spreadsheet to fill in for me, and they were extraordinarily helpful and a lot quicker than the UK HFEA that we also have the data from. And when I asked them what are the embryos that are transferred with and without PGS on an age range basis, you can see here that in all categories, there does seem to be an improved live birth rate on a big data basis, except for the less than 35 age group. And that message is coming out in quite a few studies, in that if we really are interested in looking at aneuploidy embryos, it will probably make a difference. And again, it's argued at what level that difference is. And I'll come on to that in a second. But there is a significant difference overall after the age of 35 if you're putting back a single euploid embryo. And what evidence is out there at the moment? Well, there are meta-analyses. As you can see here, there are 3 meta-analyses that have looked at the opportunity of deselecting aneuploid embryos. And I'm talking about aneuploid embryos. I'm not mixing the argument here where mosaicism is sometimes implied as being abnormal, whereas we know mosaicism is a sort of grey area and an issue. I'm talking about simple binary comparison between aneuploid and euploid. And there have been individual studies as distinct from the meta-analyses. And, of course, most of these are on the basis of embryo transfer because these studies are designed to look at embryos. They're not designed to look at the patient because of the great variability in patients. And I'll come on to that in another study briefly. But what I would like to draw attention to is just the one by Scott et al. In 2013, because this particular study, is, as you see here, as it was entitled in the fertility and sterility paper, did actually look at intention to treat. It was a randomized study, computer-based random number generation. It had block-up randomization in addition, and that's very important because that selected out each age group, so there was a control representative in each group, so that normalized the equivalence of controls. And it was a registered clinical trial. And what they found in this particular study was, and this is just on the outcome per treatment cycle, was that there was a statistical significant difference between those where PGS was used and those cycles where PGS was not used. And I don't know whether you can see it on the right-hand side. This is, according to evidence-based medicine, is a class 1 trial, and that is based on intention to treat. And then we have the more recent Illumina trial, and this is, Illumina trial was one of the examples of why it's difficult to do these trials. Pasquale gave an example this morning in relation to the ESTEEM trial, which took 9 years in the making, and the outcome of that trial is at best data that is very difficult to make head or tail of because there are so many problems with that trial. In fact, what has finally been published had very little bearing on the original outset of the trial. After 9 years, which in many ways is a bit like saying to a woman who asks you for a termination, it's not a problem, come back in 10 months' time. Because the technology has moved on so dramatically in those 9 years. And so we see here in the Illumina study, it was I think it's a $3 or $4 million study. I don't know exactly. Whereas the ESTEEM, apart from the cost, was an extremely difficult one to recruit into. And that's one of the reasons it took so long. And there are many problems with that, which I'm not going to go into now. But in terms of the Illumina data as we have it at the moment, we know that over 35-year age group, which funnily enough fits in directly with the big SART data, there was an improvement in live birth rate, up about 36.5%. in the PGS versus the control arm. Now, again, admittedly, this is based on embryo transfer. We need to see the data on per cycle started, and we need to see the publication on that, and we are awaiting that. But there are many, just the point I'm trying to make, who believe that if we do use this technology, we can shift the 70% of embryos transferred without that technology that are unlikely to make babies to 70% that have the opportunity to make a baby. So we can flip it if we use that technology. But, of course, it's an invasive technique, and it's an expensive technique. And, in fact, I think the interesting debate to have with PGT-A would be if you weren't actually charging for it, would people then believe it might be worth using, which flips the kind of ethics and the positioning of it quite sharply. So there's been a drive, obviously, to try to use non-invasive techniques. Metabolomics, I still think there's quite a way to go, but there's some very interesting data coming out on metabolomics. Cell-free DNA, I don't know whether that's going to get off the ground. Again, there was some mention of it this morning. I, too, have great worries about cell-free DNA, and I think there's a long way to go before one can actually show conformity and consistency between that and what you will actually find, for example, in the inner cell mass tissue. Simply because of the degeneration that you get, whether it's in the blastocelic cavity or in the culture medium. But I think there are some studies that are coming on which may prove interesting in the not too distant future. For example, biomechanics and developmental potential of oocytes and embryos. There's quite a bit of work now being done in academic institutions on the biomechanical properties of embryos, viscoelasticity of the oolemma and the blastocyst indeed. And that's been related, the biomechanics of that, to embryo viability. And I think we will see more coming on biomechanics of embryos excuse me, in the not too distant future. There's another area of great, as well of great interest, which is optical coherence tomography, or optical coherence microscopy. And this is this is an interesting paper. And it's a very intriguing research profile for embryos, because we can measure the internal motion of cytoplasmic activity, and you can use high-resolution intracellular time-lapse with this. And one of the things you can get out of it, amongst some many other interesting observations, is a non-invasive cell count in real time. And of course, we know from our studies of taking embryos out from in vivo growth, comparing it to in vitro growth. We know on many other studies looking at the viability of animal embryos, actually cell count is extremely important. And so this technology may be of use in the coming years, I was going to say, but simply because driving these technologies into clinical practice is not easy. I'm going to show you an example of that very specifically shortly. Clearly an area that's moving quite rapidly and has, again, its detractors, but also its supporters, is time-lapse imaging. And here's Zenovich's article in Fertility and Sterility 2017 reviewing time-lapse imaging, said the following, that it has great potential for enhancing embryo selection. It enhances conventional morphological assessments. It detects several morphological phenomena that are often missed with static observations using conventional incubators. Morphokinetic parameters can aid in differentiating between euploid and aneuploid embryos. I'm not sure I entirely agree with that, but you would never use it clinically, because it may have the ability to distinguish the difference between gross aneuploid embryos, but it's certainly not going to have the binary potential in subtle or even significant ones, such as those that go to term, an aneuploid 13, 18, or 21, for example. But his overall conclusion is that a compelling body of evidence has shown that time-lapse imaging, especially when combined with standard morphological assessment, can improve embryo selection. So I want to take you on to our own data, because it's our personal experience. And we've worked now for nearly 10 years on time-lapse imaging. We've looked at a vast range of potential algorithms. And in fact, the one we settled on is related towards the blastulation end, and a few algorithms actually focusing on blastulation. And that is the kind of morphokinetic dimension that you can use with time-lapse imaging. But we also know very well that we can see dysmorphism in cleavage that you would not see if you had conventional incubation, and you would not actually use in the algorithm that, for example, if it was to blastulation or day 3, because it's a completely different measurement that can give you information about that embryo. And I'll give you an example here. Probably many of you have seen this now, but I'm going to show you again. It's an example we see quite a lot, is what we call the reverse cleavage. If it works, it worked in the speaker's room.
It's working.
Oh, is it working? Yeah. Oh, you just can't see it on here. Okay. If you look down the bottom right-hand side, you will see the time, and you will see when it divides, it then, I can't see what it is, but anyway, it goes back to the 1 cell. Then it divides again It ends up as a beautiful 4-cell. So you can imagine in conventional embryology, you take it out at pronuclear stage. You see the pronuclei. You put it back. You come 40-odd hours later, and you see a beautiful 4-cell. You're very happy with that embryo. It divides to the blastocyst. You transfer it. We now know, and as we've published in our atlas, there are many of these anomalies which have a very low rate to almost a zero chance of making a baby if particular ones of these dysmorphic events are visualized, but you have to visualize them. You have to be able to go through all the video timings to be able to see if you we can get some of the morphokinetic algorithms that actually are fine. It's just that they've got these problems upstream. So you need to be able to see them. The second problem I think people are having with time-lapse imaging is actually the control, the quality assurance that happens between the embryologists who are doing the annotating. This is extremely important. So not only do you have to control your environment, you have to actually have the people who are doing the annotating extremely tightly controlled. And we do this in our organization. Every one of our embryologists, this is just an example here, must be able to go through a strict quality control. The coefficient of intrapersonal variation has got to be very tight. For example, we would put up here at least around about a 90% plus agreement before they'll be allowed to annotate clinically. And I think, again, that is quite important in laboratories that have more than one embryologist who are undertaking time-lapse imaging. So let me just take you through our recent publications in this. The first question we asked, well, if we compare time-lapse embryology to standard incubation, do we see any evidence of a difference in live birth rate? Live birth rate for us is important, not clinical pregnancy rate, live birth rate. So the first question you have to ask, which is what I find quite annoying about what we see in the literature today, when people just do simple chi-squareds or some of the simple statistical analysis on implantation or live birth versus no live birth, is when you put an embryo back into the woman, she now is in control as well of implantation, as well as the embryo. So it's not just all about the embryo once you transfer it. So what we did was, first of all, we took every single piece of data that we had that was relevant. We didn't bother with the address of the patient and such like, but everything we thought might be clinically relevant. And we analyzed every single one of these, or we gave it to independent statisticians who are not in our field, but we gave them the data set to independently assess this for us on the basis of all the female characteristics. And the interesting thing they came up with, first of all, was everything in bold that you see on this slide actually had an impact. So unless these are accounted for in the statistical analysis, you can't just add in live birth, yes, live birth, no. It's what are all the female parameters, and these are the ones in bold that you have to account for at the very least, that is going to assure you of a reasonable statistical analysis once the embryo has been transferred. Fine if you want to analyze up to blastulation rate. But as far as we were concerned, predicting blastulation was rather irrelevant because how many blastocysts don't make babies? So in terms of the analysis, we had 24,000 records of treatment, 21,000 plus standard incubations and over 2,500 time-lapse data and nearly 15,000 unique patients. I won't go into the stats, but what do we find? That almost in every event, there was a statistical difference in women under the age of 38 in terms of live birth events, so delivery, except for biochemical loss and clinical miscarriage. We actually found no difference in our study in relation to those two. But in terms of every other aspect, in terms of a live birth event or a baby per embryo transferred, we found that there was a highly significant difference. In fact, so much so that if we compared the overall of all the different types of embryos, we saw a 19% uplift in live birth rate, and if it was just the blastocyst being transferred, it was a 25% uplift in live birth rate. It wasn't significant in women over the age of 37, and classically, I think that would probably be largely in part due to the aneuploidy that one sees in that older age group. So then we asked a second question. That is just and Pasquale said it very clearly this morning, one really needs a randomized controlled trial just to see if the incubator is important and the closed incubation system rather than actually the algorithm. So we kind of asked this in another way. We asked whether or not we could select embryos using time-lapse imaging on the basis that can we grade them? Can we put them into some sort of hierarchy? And would there be a difference between the outcome in live birth depending on the classification of the particular embryo? So we looked at ranking them. And really, just to put this into simple terms, we ranked them into 4 categories, and you could see at the top left, I'm not going to go into the detail here. These were the algorithms that we used, and when we transfer our embryos, the machine gives for the embryologist a ranking of the embryo. And we found, as you can see here, there seemed to be a highly significant difference between a grade A embryo and a grade B and the other embryos. There was a reduction in miscarriage, and it was significant, but it's not something I'm playing a large account to at the moment. But I do think that the live birth rate, if a patient, and they may not have, just like they might not have a euploid, they may not have a grade A embryo. But if they have a grade A embryo and you transfer that back, the chances of a live birth is significantly higher than any other embryo. And in fact, what we asked our statisticians to do was to start to compare every other single embryo comparison that you can do, which they've done here. And interestingly, if you take the big distinction between an A and a D embryo, the A had a 233% chance of a live birth compared to a D. So we felt, and this is comparison within the same system. This is not comparing standard incubation to time-lapse. This is ranking embryos within the same system. So then we asked a very simple question, and that is, well, okay, if you're going to do your conventional morphology, what embryo would you, and every embryologist, I think every embryologist in the audience would say, we'll put back a classic Gardner AA, or what we call a 1-1. And you do a 1-1 before you do a 1-2, and before you do a 2-2. And so we asked our database, because there is a different objective hierarchical ranking by the computer, and then there's the embryologist morphological score. And what do we find? Well, actually, the best embryo to transfer was a 2-2, or a BB. That gave us the highest live birth rate. And so we have to say, well, that's evidence, isn't it? Don't you believe it? And, of course, I say, no, it's rubbish. And why is it rubbish? Because we don't know what the embryo is going to be in an hour's time. We don't know what it was an hour before the embryologist scored it. So all it's doing is simply proving the subjectivity of morphological assessment versus perhaps an objectivity when you're using an algorithm. So we went on to do another study. And this is not yet published, but it is being written up. We just wanted to look at a single set of blastocyst single embryo transfer embryos. And this was in 679 live births. It was a 50% live birth rate. And we simply compared the embryologist morphological assessment versus the computer's hierarchical ranking. And what do we find? Well, you can see here that the live birth rate versus morphological grade had a clear ranking system, as I've already showed you. When we overlay that with morphology, what you could see here in this data set was that actually it was extraordinarily blurred, and there was a non-significant difference in the particular sort of top ranking of embryos. So if the embryologist had a grade A embryo, but it was an AA, a grade D embryo, or any of the grades by Morphokinetics, and they didn't know what the morphokinetic was, and they would choose, let's say, an AA or an AB, that may not necessarily be the embryo that's going to give them the best chance. But it's classical embryology, and that's why we do it. And if you actually look at the ROC curve in relation to comparing morphokinetics to morphology, it was clear to us that there was strong evidence of the superiority of embryo rank model compared to the transfer grade model. So moving on, Others have been looking at potential other biomarkers and other opportunities. Mitochondrial DNA quantity, for example, especially the work of Fraguli and Dagan-Wells. And Dagan-Wells published a recent paper here looking at mitochondrial DNA. Now, I think all of us still, I say all of us is wrong, but many of us still think this is a very controversial area. And in his paper, he says chromosomal status is the most definitive for embryonic potential. Well, I think that's true, certainly, if you're comparing it to mitochondrial assays. This is the only one factor amongst many of the relevance of embryo viability, as evidenced by the fact that even the transfer of a chromosomally normal embryo cannot guarantee a pregnancy, of which we are very well aware. But for me, it's still about the embryo. It may just not be about the chromosomes. I think the algorithms may have some genetic input as well. There can be many other aspects relating, and that's why, irrespective of what the female physiology is, and that's not the embryo, of course, you will still have embryos, even though they are euploid, that may not be able to implant, even if you had the best uterine environment. So that's why, for example, people are searching for other biomarkers, especially of the endometrium. Now, it's kind of more clinical, so I'm sure Norbert may go into this. This is not for my talk, but actually we shouldn't forget the earlier work of Chan, and then of course the work of Carlos Simon, two separate. The early study is listed there in fertility and sterility, who found a whole load of genes, anywhere from 50 to 60 specific genes about endometrial receptivity. And, of course, we still need to understand those genes and find physiology for them. But yeah, these are attempts to improve what we do. But this is a very interesting study, as we see here from Wu and colleagues. And I think this is an important study. And it was looking at perinatal outcomes after natural conception versus in vitro fertilization. And it was using a gestational model. So the surrogate had antecedent pregnancies naturally as a control. And what they found was that if they then had an IVF embryo transferred, there were several adverse outcomes. Lower gestational age at delivery, higher rate of preterm delivery, lower birth weight, increase in adverse maternal outcome, including gestational diabetes and hypertension. And they concluded that assisted reproductive procedures may affect embryo quality and that its negative impact cannot be overcome even with proven healthy uterine environment. And they further concluded that it's iatrogenic or genetic physiology in specific patient populations. Now, I actually have some agreement with their conclusion, but I think there are some other factors too. It may still be embryo, inherent embryo, or patient-to-embryo problems that are not the ART technologies per se. And that's why I go on to one further study that we've been doing, which isn't particularly embryo, but it is associated with the embryo. And I want to talk about this haplotype, the annexin A5 M2 haplotype. So it is part of the annexin proteins, and A5 is, as you well know, to do with clotting. And the M2 haplotype is a 4 base pair mutation, and it causes a reduction in the presence of annexin. Now, it's normally present in high concentration on the apical surface of syncytia trophoblasts. But if you have the presence of the 4 base pair mutation, you have a risk giving you hypercoagulation. And there are now several publications, there's 29, demonstrating the association with pregnancy outcome complications from miscarriage to small for dates babies to gestational hypertension, all the things mentioned in that previous publication by Wu. And there's a good review of the annexin A5 itself by Bhutia in 2000 and colleagues in 2015. So we've been interested in this particular mutation in our IVF cohort. And it's been studied now in over 4,500 patients of different ethnicities. And there's a whole raft of obstetric complications. But a carrier of the M2 haplotype is very different to conventional thrombophilic disease. And the carriers are at risk 2.4 to 4.0 of various thrombophilia-related phenotypes. You can see here that there's an M1 and an M2 haplotype. The bottom one is the M2 haplotype, which is the 4 base pair mutation. What is really important about this work is, first of all, it's conveyed embryonally. So if the man has got this mutation, it can be conveyed to the embryo, and therefore the embryo or the pregnancy is at risk, even if the woman hasn't got the mutation. Did it come up? No, okay. The risk is independent of maternal and paternal transmission, and it's distinct from other thrombophilic disorders. And as I've said before, it has a whole spectrum of lesions or pathologies in the placenta. So we studied this, and first of all, we found that in our IVF cohort, and this was published in 2014, that its prevalence was variable in a variety of groups, but it was almost equally present in men and women. Only about 10% it carried in both partners. But it was also present in 37% of our unexplained infertility, and it was present in 35% of our PCOS patients. And so what we did in these couples that had miscarriage or placental problems, we treated them with low molecular weight heparin. And what we found in doing that, and this is published in Lancet's eBiomedicine online, was that the couples that had no treatment and were at risk of miscarriage on the left-hand graph here, there was very few live birth rates, clearly, and those who were treated with low molecular weight heparin actually went on to have a chance of a live birth at an equal status to our control group. So again, a biomarker that is a very different type of biomarker that we think can aid in the maintenance of the pregnancy. I want to move on now to something quite different. And again, this is looking back embryonally, and it's looking back into a potential marker of the development of the fertilized embryo. And I was absolutely delighted that Jerry Shatton raised the issue about polarity, because I think these studies are informative of how polarity is actually conveyed at the very outset. And so what we see here, you will see down at the, if this video works, you will see down around about 5 o'clock, the extrusion of the second polar body. But what I want you to just look at as this is happening, is it? Yeah. Just look at the movement of the cytoplasm as the polar body is being extruded. And this is from the moment of fertilization. And you can see the movement of that cytoplasm is active and really very intense. I'm just trying to see if it's finished. But anyway, you've got the idea. So we mentioned earlier about the... Is that the same one? Okay.
Hit the restart.
Okay.
Then.
Yep.
Okay.
So we spoke earlier, and Jerry showed this very clearly, about calcium oscillations. And we can see in the left-hand video here cells with calcium oscillations that can be measured. But if we look here on the right-hand side, now this is the oocyte, the ooplasm, once it has been fertilized, and this is a mouse embryo. I'm going to show you here. The one I showed you before was a human oocyte. Sorry, it's not a mouse embryo, it's a mouse oocyte, because it's got the fertilization cone that you can see at the top about 11 o'clock. But the other one was a human oocyte. Now, if you look here, is that moving? Is it?
Yes.
Okay, so we can actually detect now through particle imaging velocimetry software the actual movement of the cytoplasm. And you get these dramatic periodic increases and decreases in the velocity of the cytoplasmic movement and its directionality. And these are being given the interesting name of speed peaks. And this work was done in mice, as we see here, by Ajak et al. And co-workers that we work with from Cambridge. And they published a fantastic Nature study that you should have a look at, which studied the whole of these movements and the origin of these movements and the control of these movements and how they relate to viability of embryos. And it's all following sperm entry into the ooplasm, a bit like the debate we had earlier before this session. First of all, it's based on the contractions of actinomycin cytoskeleton, triggered by calcium oscillations. And we now know that the calcium oscillations alone are not enough to induce the right actinomycin cytoskeletal movements. So again, a slight issue if you're just using calcium triggers. An analysis of the cytoplasmic oscillations and movements predict the developmental potential of the zygote. This could be the earliest and fastest non-invasive way to predict the viability of eggs fertilized in vitro. I'm running out of time, so very simply to say that this is a schematic cross-correlation. So what you do is you take an image of the movement of the cytoplasm, and then you interrogate different regions within the regions of the cytoplasm, so you get cross-correlation between subregions, and then each one is divided into an individual square, and you get a coefficient of distribution between the particular images. The point is, using this, you get a displacement vector. And that's the critical thing. This displacement vector gives you an amplitude and speed of movement of the cytoplasm in a particular direction, as you saw in the previous video. And therefore, the possibility here is to very accurately measure the subpixel movement. This is just a brief example of, you can see across the top in the fertilization stages. At the M2 stage, there's very little cytoplasmic activity. Once fertilization happens, you see that the mean cytoplasmic speed can be represented, as you can see here in the chart below. And for each of those stages, very precise measurements have now been obtained, and you can see this here in this diagram. You can get interference contrast images with vector patterns, and they're represented for the representative of the different stages. The length of the vectors and the color of the background indicate the speed of the local cytoplasmic movement. And what has been fascinating about this is that they have now used this technology to prove, almost beyond doubt, that in the mouse, you can predict which oocyte, having been fertilized, is likely to give you a live pup, or is likely to go on to produce the best live pup in terms of its developmental capacity. So maybe this very early on, non-invasive imaging, which we are now doing in human oocytes, could be helpful in also predicting embryo viability. Just to finish off with, where else are we going in embryology? I think robotics is going to be introduced probably in the not-too-distant future, robotic ICSI perhaps, and robotics in other areas. Again, what are we trying to do? Remove subjectivity, create consistency and objectivity in our human embryology work. Also, our environment for culturing the embryos, something that was said earlier today by one of our esteemed colleagues, that we should be growing the embryos to the blastocyst because we get better outcomes. Well, we kind of know that, but it's almost a self-fulfilling prophecy, because we can't do the experiment that says, had we got the day 3 back earlier, it would have been just as good. It's just that it's subject, for some reason, to sensitivities of its particular culture environment. So I think we need to change the way we culture embryos, and I think microfluidics and specific culturing technologies are going to change too. And finally, maybe we will be moving away anyway from an in vitro culture and potentially moving to an in vivo culturing system. And this in vivo device is being developed, and we worked with these guys 10 years ago, and we're still working with them. And it's a fascinating device that allows the interaction between the embryo and the uterine tract during the post-fertilization cleavage period, which allows the embryo to develop in vivo and be removed, or the embryos, if you've got a lot of eggs, and be removed, and then you transfer your single blastocyst. But it's been cultured in vivo. And of course, if epigenetics and other aspects are an issue, the data we've got at the moment is that you have a higher cell number if you do culture in vivo, then, and we know that that's also predictive of outcome, then it may well be that in the near term, we will be looking, at least for some patients, for an in vivo approach to our embryology. So just to finish off with what's our own organization strategy, we'll do time-lapse imaging for all patients under 38. We will do aneuploidy testing because of its high prevalence in women over the age of 37. And we don't think that the time-lapse imaging and the aneuploidy are actually mutually exclusive, because we've seen many euploid embryos that have upstream a dysmorphic cleavage pattern, and that itself is indicative of a low percentage outcome of live birth. But moving on to personalized genetics is the way forward, I think. And it's one of the reasons why lots of large RCTs potentially fail, because they're not stratifying the patients who actually need the treatment you're offering. And that's why it's very important for us to keep trying, to keep looking, and to keep finding ways of making what we do efficient. And I apologize very much to our Mandarin speakers if I've actually interpreted wrongly the concept of personalized medicine in this slide. Thank you very much.